Interesting. So it's my pleasure today to present this work. It's the result of almost a year and a half of work on the Hunga-Tonga seismic data. And so today I'm going to present what happened on the 2022 eruption under the lens of seismology, using as much as seismic information as we can to try to understand what happened on the volcano, what's the origin of the seismic signal, and what type of source model we can use to better characterize what happened on this day. So this is a work that's co-authored with my colleagues Carl Tape at the University of Alaska Fairbanks and Ryan Modrak at Los Alamos National Lab. And so we're going to talk about seismic data, inverse problem, moment tensor, and point force inversion. But before we delve into that, I'd like to give a brief introduction on what happened on the island formerly known as Hunga-Tonga, Hunga-Hapai. So this island was, because it has been split in half, the summit of an underwater caldera, the caldera of an underwater volcano that's located roughly 60 kilometers north of Nuku'alofa, which is the capital city of the Kingdom of Tonga. So it's about here. It's in the Tonga, on the small Tonga plate along the Tonga-Kermadec subduction in the Pacific Ocean. And so this is what remains of the island after the eruption of January 15. So it's a large underwater volcano, and it was known to be active for at least since the end of December of 2021. So the geological services of Tonga were reporting on the numerous explosions that they were observing at the Hunga-Tonga, Hunga-Hapai Island. And there's also a lot of infrasound, hydroacoustic and seismic signal that were picked up by CT-BTO and IMS. So you can see here, we can see a lot of infrasound activity that's been recorded through December. It started to recede a bit at the beginning of January, but basically we have 4 weeks of mild seismic volcanic activity before we have the big event on January 15. And so it took a bit everybody by surprise, because you can see that the rates of events were starting to get slower and slower until everything basically exploded in a very cataclysmic way. And talking about January 15, there's a few facts that makes this event very spectacular and unique. And one of them is the fact that we have a wealth of sensor that has observed and recorded this eruption. So it was a long eruption. It lasted, the geophysical signal lasted several days when we count the atmospheric disturbances. We have the chance to have a lot of seismic stations and barometers around the world that recorded the signals, GNSS stations as well, buoys that recorded the tsunami, both in the Pacific and in other oceans, and some hydrophones data. We also had the chance to have several geostationary satellites that were observing the Tonga from different angles, and that were used to do some stereographic analysis of the plume as it went up in the sky. And so really this is a remarkable event when we consider that it's the largest explosive eruption of this kind within the modern instrumentation era. When it comes to the geophysical feature that manifested during this day, one of the first one that I got exposed to, mostly when I saw pictures on news outlets and social media, were the ash plume. So if you're on the internet on January 15, 16, you probably have seen a lot of those pictures where we can see the plume from the either the GOES-17 satellite or the Himauri satellite. It has been measured to pierce the lower mesosphere, so at a height of approximately 58 kilometers altitude. In case you haven't seen those type of animation, here it is. So it's one image every 10 minutes from the GOES-17 satellite. Along with this ash plume, which is believed to be the highest ever recorded, we have also tsunami in the region. So the nearby tsunami reached a height of 12 meters when it reached the Kingdom of Tonga. So it caused a lot of damage and it affected profoundly the Kingdom of Tonga. And it's responsible for a few loss of lives in the Kingdom of Tonga and across the Pacific Ocean. And the third large manifestation of this event was the atmospheric signal that was being recorded by infrasound station and barometric station across the globe. The eruption was so violent that it basically shook the whole atmosphere like it was a bell, and we saw those pressure perturbation circling the Earth several times. So it's been recorded at least 3 times in most stations across the globe. It was also accompanied by an audible sound that was heard all the way up to the Yukon territory, almost 10,000 kilometers away from the island of Tonga. So quite spectacular and quite violent interaction with the atmosphere. The atmosphere was also strongly coupled with the oceanic systems, and it was responsible, this land wave was responsible for propagation of tsunami across continents. And we were able to record some small tsunami measurements in the Atlantic that basically hopped the American continent. And finally, we have some global seismic excitation. So here I've plotted a record section of the vertical component displacement from 0 to almost 100 degrees distance. And so the layout of the talk today is going to be the following. We're going to first just look at the datasets, look at this record section, and try to see exactly what's inside of it and what we can tell just at looking at the data without doing any further advanced processing. Then we're going to talk about the 2 main models that we came up with to explain the sequence of events that were generated during this seismic excitation. Then we'll talk a bit about source inversion, of course, and about the ambiguity between the 2 source model that we ended up with. So let's jump in the data sets. So back to this record section. There's a few things that are very striking when we look at the record section. The first thing is that there's almost no P-wave data or close by body waves data within 40 degrees distance, which is quite a long distance. So of course we are in the context where we are in the middle of the Pacific, so we don't have that many stations, but still it's kind of remarkable that we don't have any strong body wave excitation close by. If you have a keen eye, you'll also see that there's potentially at least 2 different wave packets inside of this record section. So here, if we look at some teleseismic body wave, there's the first arrival, and followed after, there's a second wave packet, which has the exact same move out and has this constant difference from the first break. And it's also fairly visible in the surface wave data. We can also see a hint of it in the S wave here. Another thing that's very exciting about those seismic data is that it's excited both the vertical radial component. Of course, it's a bit more noisy, but we have some beautiful S waves here, and we can still see the surface wave with those 2 wave packets and some love waves on the transverse component. So we have fairly strong transverse signal all across the network. Because it was difficult to work with both the teleseismic P waves and the surface wave at the same time, what we decided is that we're going to split the dataset in half, with first teleseismic datasets where we thought that we had enough energy, and the regional surface wave, so everything between 0 and 30 degrees distance. And for this one, we're going to work on the body waves because we have a clear signal, and the surface wave here are starting to get a bit fuzzy because of the long distance of propagation. And here, because we don't have body wave to work with, we work with only the regional surface wave. So here are the map of the 2 acquisition setup we have. We have all the teleseismic stations, so we have a pretty good azimuthal coverage. It's a bit short of 150 stations all across. And here we have the regional surface wave. So most of the stations are coming from either the geoscope network or the global seismographic network, and a few stations from the New Zealand network and the Australian network. And they've been very instrumental in being able to tell something about this source. If we zoom in the teleseismic P wave, and if we align all of the first arrival with the theoretical P wave arrival time, we end up with this record section where everything is fairly well aligned. And there's something that's very striking that you can see when we look at this arrival that's visible in both the vertical and radial components. Mind the noise here, is that we have a fairly consistent signal all across the network. So all across distances and azimuth, we have almost the same signature. And this seems to indicate that the source is probably axisymmetric. And the good news is that there's not that many seismic source types that are perfectly axisymmetric. It's actually a small subset of all possible seismic sources. So the couple of models that could explain those type of data would be vertical forces, either downward or upward, or an explosive moment tensor, or an implosive moment tensor, and some vertical CLVDs. And here we also have the second wave packet, which is a bit longer than this one. And although it's a bit more difficult to tell, we can see it's also fairly coherent. So potentially there's a repeated processes that generated both the first and the second wave packets. And finally, we have a guest on the record section here with this very badly timed surface wave arrival that's arrived exactly in the first sub-event of the sequence arrival time. So the problem with this is that when you're going to stack to the seismic record section, this guy is going to probably creep in and make a couple of interference with your teleseismic stacks. Now moving on to the two different models. So we're mostly going to talk about downward force and explosive moment tensor. The reason why we're not going to talk too much about implosion or upward forces is that all the results that you're going to see today that we obtain through estimation with using waveform misfits and inversion approaches have been found to be either downward forces or explosion. And so how might they be explained in terms of what happened on the volcano? So here we have two sketch cross-section of the volcano. You can see it's quite a steep slope underwater, and the top of the caldera sits very shallowly underwater. And for the force model, what is generally accepted is that you're going to have a raise in pressure of material inside of the magmatic chamber. So this material is going to get with a very high pressure until there's a limit where it breaks the cap. And when the caps get broken, it's going to jet a lot of the material that was inside of this highly pressurized cavity into the atmosphere. And because you changed the system, you're going from an enclosed underground system into the atmosphere, there's kind of a discharge. And so necessarily you have a reaction force to get to the equilibrium that's going to act on the top of the volcano and going to push everything downward. In terms of the moment tensor, it's also likely that if we have an explosion, it could be the result of phreatomagmatic activity, where as the eruption goes on, you're going to have more and more fractures inside of the top of the caldera with more infiltration of water, more interaction between water and hot material, releases a lot of steam, until potentially there's a chain reaction and it explodes into all directions like a proper explosion. In terms of their mathematical representation, the point force is simply a 3-force vector, where the total magnitude of the force is just given by the contribution in each direction. And the explosion is represented as a 3x3 symmetric moment tensor that you might be familiar with if you are doing a lot of source studies with seismology. In our group, what we like to do is, instead of using those 3x3 tensor directly and using all those mxx, myy, and mzz values, instead we use a different parameterization when we search for best fitting moment tensor for a seismic source. And we use the tape and tape 2012 parameterization, which recast everything in terms of source type, which correspond to the colatitude and longitude on this Loon diagram, and orientation. So here we have a typical double couple moment tensor represented as a focal mechanism, a beach ball pattern, where you can see the motion on one of the fold plane. And here you have the Loon diagram with a fixed orientation, and where the moment tensor shape and thus the motion only changes according to the position on the Loon. So it means that for every source type, there's that many different source orientation. And why we like this is that it's very well-founded in terms of geometrical properties of the moment tensor, and it's also very helpful to help discriminate between exotic events such as explosion or implosion. So all of those white beach balls here would be implosion, all of the energy going inward. All the beach balls above this line here are all explosions of different kind. And everything in between are earthquakes, with the double couple being exactly at the center of the loop. So this is a very handy diagram and a very handy representation when we try to discriminate different source types. And now we move on to the source inversion. So here we have a plan of attack on how we're going to study these events. The first thing is that we're going to take advantage that the first sub-event seems to be fairly well separated with the rest of the sequence. The nice thing is that we see that there's one thing here, while here it's a bit difficult to tell exactly what's going to happen here. So the first step of our study is to characterize what happened on sub-event number 1. So for this, we're going to do a typical moment tensor inversion using a grid search method, and we're going to also test different force scenario. And then once we have this, because we have this hypothesis that perhaps this is a repeated process that generated both those two wave packets, we're going to try to invert for the source time function of the sequence, basically the timing of what happened if we had a repeated source. And finally, we're going to try to invert for everything all at once, meaning the source type, the onset time, and relative magnitude of each of the sub-events of the sequence, using all the possible information we have and using a black box optimization method. So let's get to step 1 first. So the way we usually do moment tensor inversion is using waveform-based misfits. So it's going to be thought as a misfit minimization procedure where we're going to try to minimize the misfit between synthetics here in red and observed data in black. And the way we do this is that we're going to simply have a grid search method, which is just a brute force approach, where we're going to try every possible location on the balloon, so every source type. And for each of those source types, we're going to try to test all the orientation possibles. So it can be very cost intensive if you want a very fine grid, because every time you add a grid point, you're going to have to consider all of the other parameters as well. In general, to speed up things, we work with a simple 1D model from which we can get Green's function fairly easily. And then the synthetics are just computed from those pre-computed sets of Green's function by a linear combination between the source type and the 1D model response. And so we're just going to try and get several locations on the balloon, so several different source types, several different orientation. And basically, we're happy when we see the synthetics match the observed data. So this is a very rough and very quick explanation of how it works. In application, what we're going to do is that we're really going to try every single position on the balloon and as much as we can afford. So we can quickly go up to several 100,000 grid points to potentially more than 1 billion parameters. And we apply this method to both data sets for the Hunga-Tonga, the teleseismic P waves and the surface wave. And we end up with those solutions. So here we work at a fixed depth of 1 kilometer. We have the moment tensor results and the point force results. So let's go through first the moment tensor misfit. So now that we've mapped the misfit here and we found that the solution is here, we can say that it's likely that the source that explains the P wave is an explosion. We remark that it could also be an implosion because we also have a low misfit value here. As for the force misfit, the figure reads a bit differently. Here you have to imagine that this is a unit sphere, and the piercing point of the best fitting force vector is denoted by this green circle. So this means that here we have up, down, the south is here, east, north, that wraps around, and west. And so here the best fitting force is a downward force that has east-north plunge. If we move to the surface wave, we have kind of a similar scenario where the best fitting moment tensor is also an explosion. We have this low misfit swath that is very reminiscent of nuclear test moment tensor inversion. And this is likely due to the very shallow nature of the event. And for this, the point force here, we also have a downward force, but now with a different orientation with to the northwest. So the good thing is that even if we have slightly different explosion and slightly different point forces, we're happy because they are consistent in terms of their polarity. Both source model, we're going to apply the same orientation of pressure on the ground. So the force is going to press down on it, and the explosion is going to also send energy, radiate energy downward. So they are consistent in terms of their polarity. And so now that we've seen at the misfit, let's look a bit at the waveform fit. So this is the waveform fit for the first sub-events for the best moment tensor solution. So you can see that the Rayleigh wave, so here we have a vertical radial component, vertical radial. The Rayleigh wave all across the regional surface wave network is fairly well constrained. And we also have some good results on the love wave. And here it's the results of the point force inversion. So we have kind of a similar waveform misfit. It's actually slightly better for the moment tensor, but if we had the space to look at the body wave results, the force then has a slight advantage on the moment tensor. So by just judging at the waveform fit for the first sub-event, the two source model are almost even. Now that we figure out what the first model is likely to be, which is either downward force or an explosion, we're going to try to see if we can find what happened during the whole sequence of sub-events. So we have this hypothesis that we have the repeated source. So we're going to use the source that we got previously, and we're going to try to find potentially 5 different sub-events spanning a bit less than 400 seconds. And to do that, instead of doing the grid search, we're going to use a black box optimization method called the covariance matrix adaptation evolution strategy, so the CMAES. It's black box not because we don't know what's happening, but because it requires little tuning and almost no hyperparameters. It's based on Gaussian sampling, and it basically adapts the search direction and search spacing with successive samplings. It's gradient-free and embarrassingly parallel, and it's very well designed for those type of problem with less than 100 unknown. So let's say we want to find what's the minimum of this dummy misfit value, and we want to find this white triangle. So the CMAES, with the CMAES, we're going to start with an initial random spot on the misfit, and we're going to draw some random sample according to a Gaussian distribution. Because it is an evolutionary strategy, we're going to prune half of the population, test only the 50% best samples, and we rank them by their performance or low misfit. So what this allows us to do is that with respect to the initial guess, it gives us basically the overall direction of where the misfit gets better. And this allows us to adapt the size of the covariance matrix from which we're going to draw the next generation. And once we have adapted this, we move this distribution according to the weighted combination of those best ranking samples. And then we draw a new population and so on and so forth. So what this algorithm does is that it has a tendency to first cast a wide net. And once you stumble upon a place where it's going to basically get stuck in the minimum, it's going to sample mostly the basin of attraction, which means that you focus a lot of computational energy into those lower misfit region. So it's not a global optimization method. It's not going to try to sample the whole space, but it's very fast, which means that if you are smart about where you initialize your sampling, you potentially can have a good overall guess of what the whole misfit looks like. And so we apply that to our problem of trying to estimate the sequence of explosion. So what we do here is that we create this source time function that is a sum of Gaussian, and we're going to initialize it with 5 random Gaussian peaks at different locations and different amplitudes. And the CMAES is going to try to find the best combination that minimizes the misfit between the observed and the synthetic data. So as it goes, what you're going to see is that at some point, 2 of the events merge into 1, and we end up with only 4 sub-events that seems to be adequate to explain those 5 stations data. And if we plug this source time function into the whole network of regional surface wave, well, we can see that it's very well adapted to fit both the first and the second order wave packet. So it's likely that we have 3 sub-events here and 1 here, and it also fits the love wave data, even though we haven't used it for the CMAES inversion. And so we end up with a scenario where it's likely that we have a repeated source with 4 sub-events. So a reality check here is to look at high frequency teleseismic stack and count the number of maxima. So here we have 4 maxima, and the nice thing is that the relative timing between each of the peak corresponds to what we have inverted in the previous experiment. And so trying to be a bit more ambitious and lift the hypothesis that it is a repeated source, we don't want to enforce this. We're going to try to invert for everything at the same time. So here is the set of station we're working with. Here is the source time function. And in this case, what we're going to do is that we initialized the origin time at random, close by the maximum that we saw in the teleseismic body waves. We don't want to search the whole space because we know more or less where the peaks are. And we're going to draw random force direction. So we initialize everything at random here. You see that they are almost horizontal, which doesn't make a lot of sense. And you see that the initial synthetics are really bad. And what's happening here is that through the iteration of our black box optimization algorithm, the CMAES is trying to minimize the waveform misfit between the observed and the synthetic data, and it's actually doing a pretty good job across the network. And we end up with 4 downward forces, which correspond to the expectation we had coming in this problem. Moving on to the moment tensor inversion. So this one is a bit more complicated because we have a bit more parameters. So here we have a total of 28 free parameters. So each of the moment tensor location on the Loon, their orientation, that's given by 3 parameters, magnitudes, the onset time, and we're going to invert that for all the 4 moment tensors. So they are also initialized at random. And once we launch the CMAES and start to iterate, they're quickly going to shoot up to the upper part of the Loon. And it seems also to indicate that we have a sequence of explosion that's very likely to explain what happened on this day. So zooming in one of the station. So here's the initial synthetics for the nuke station. And here's the final result with the point force. You can see that we've finalized the source time function. And the same thing for the moment tensor. So if we flip-flop between the two, you might say that the moment tensor is a bit better. But again, I told you that for surface wave, the moment tensor has a slight hedge, but it's not completely the case for teleseismic body waves. And so now we're left with 2 source models that seems to be very adequate to explain the regional surface wave data sets, and they also fit the teleseismic body waves. And so how do we tell one from the other? How do we know which one is the right representation of what happened on the Hunga-Tonga this day? And so I think one of the culprits here is the fact that when we look at those explosive moment tensor beach balls, they are very uninformative. It's a flat shading, it's just a colored circle, and it doesn't tell us exactly what's happening. Contrary to a typical double couple, where if you have a little bit of context, you might be able to tell where is the fault plane, what type of motion was on the fault. So this conveys a lot of information. This just tells us that all the energy radiates outward. But fortunately, the good thing with the moment tensor is that it's a purely geometrical object, and we can decompose it and basically compute its principal components. And computing the principal components of the moment tensor gives us its radiation patterns. And when we do this for the 4 moment tensor that we inverted for with the black box optimization method, we end up with those vertically elongated ellipses, which have almost the same principal direction as the force that we've recovered as well. So they are mostly vertical and also plunging toward the northwest. And so here we are either on the case where potentially we have force model that's not enough to explain what's happening, or we have the moment tensor that's trying to look like it is a force and just taking the shape of this almost dipolar release of energy. Another troubling thing is if we take the case of a true explosion, of a known explosion. So here we have some regional surface wave data for North Korean nuclear tests. So it's an underground nuclear test that occurred in September of 2017. It was also followed by a collapse. But in general, when you look at explosion seismology, all the nuclear tests are characterized with explosive moment tensor, because it seems logical to represent an explosion with a model that radiates energy in all directions. But if you plug in point force, then you end up with this type of waveform fit, which is almost equivalent. So maybe it's time that we think of how we represent explosion in seismology, especially when we are dealing with shallow sources, which come with a lot of underdetermination. And it's very troubling that here we have, for known explosion, those two source models that again are almost equivalent. And mind that we have a way better coverage here. The closest station is 300 kilometers away, and we have way much more information, and it's way sharper than for the Hunga-Tonga. And there's a bit of hope in actually the love wave signal. So I show you in the record section that the Hunga-Tonga generated a lot of transverse signal that we attribute to love waves. And the good thing is that for the point force model and for moment tensor model, they have very different radiation patterns. The point force being a dipole, it's going to have those two lobed radiation patterns. And the moment tensor being a much more complicated combination of forces exerted on a point, will tend to generate those four-lobed radiation patterns. So, I've computed them for the best fitting force and the best fitting moment tensor for the Hunga-Tonga at 0 kilometer depth. And these are synthetics at 15 degrees distance filtered between 25 to 70 seconds. So this would be typical surface wave that we observe. And potentially, if we manage to do a lot of advanced data processing on the surface wave signal and we're able to extract the observed radiation pattern, we might be able to tell which source model is actually preferred to represent the seismic data. Another thing that gets a bit in the way of trying to understand what happened is that it seems that all of the geophysical systems that were triggered this day are a bit decoupled. So here I have the timeline of the plume height, which peaks at almost 58 kilometers. Here we have the origin of the atmospheric signal, so the big atmospheric disturbance that I showed you during the introduction. Here we have some origin for tsunamis, at least the regional tsunami that were recorded close to Tonga, and several seismic signals. So here we have different origin time, and here we have the three other sub-events that we've inverted for. And so it seemed that at 4 UTC, before everything starts, at least in terms of tsunami, seismics, and atmospheric sound, the plume is already on its way to reach the 68 kilometers. It already has started to accelerate quite a lot. And so something must have been happening already that we don't see in other geophysical systems. Here's this tsunami origin is not coupled with any other type of geophysical readings, which is a bit confusing, while this one, maybe we would be able to associate it with what happened during the main seismic sequence. And what's also troubling is that it seems that these explosions that we seem to be recording on the seismic are not the one that are related to either the loud bang that was heard everywhere all across this hemisphere, or the pressure disturbance. And if we step back a bit, what we see is that the dynamic of the plume in terms of plume height and the umbrella cloud seems also to have really started at 4, almost 15 minutes before any of the seismic, big seismic activity started, which make things a bit complicated because it means that those seismic signals that we attribute to explosion, we don't really know exactly what they correspond to in the grand scheme of things, because all of those systems seems to be decoupled. And so this leads us to the end of this story. The study of the Hunga-Tonga is made a bit difficult because we have a complex data set, but there's a lot of things inside of it. So we've seen that we've been able to model a sequence that is best explained by a repeated source, a repeat point force, or a repeated moment tensor. They are almost equivalent because of their preferential direction of energy release, which is mostly vertical with a northwest plunge. We know also that for this study, we have some limits. We work with a 1D model, which is quite simple, almost simplistic, I would say. We don't take into account bathymetry or topography. And we know that this could have effects on the generation of surface waves. And potentially, if we had a better velocity model and if we could afford to do this same study in 3D, we might be able to lift a bit of this ambiguity in the source model. We are not helped by the fact that there's no actual consensus on origin time between different authors and different geophysical systems. So we don't know exactly what we are looking at. But hopefully for this question between point force and moment tensor, there might be some hope in love wave, surface wave analysis, especially love waves, and also potentially with PDOS ratio, which is often used in explosion seismology. Also, I would like to advertise a bit the moment tensor code that we are working on, which is called MTQ. It's a combined effort with the University of Alaska, University of South Florida, Los Alamos, and the University of Toronto. Most of this work is based on it, and if you want to try your hand at moment tensor inversion, this is a great code to do so. It will do everything in terms of those Loon diagram and the parameterization that we talk about, which makes things very convenient for interpretation and uncertainty estimation. So you can access it on GitHub. There's also some material on YouTube that you can find. We gave a workshop last year, and I'd like to acknowledge all of the colleagues that made both the package possible and that also were supportive during my work and while I was staring at the Hunga-Tonga seismic data for a bit more than a year and a half. So I thank you for your attention, and I'd be glad to answer and take any questions.
Excellent. Thank you very much, Julien. Really, really interesting results there from the Hunga-Tonga eruption. We've had a couple of questions come in, and maybe I'll start with this one from Artie Rogers. It says, regarding breaking the trade-offs between force and moment tensor for shallow explosions, what strategies may improve analysis of love waves? Are there other observables like geodetic or body wave polarities that could help?
So there's one thing. Thanks for your question, Artie. There's a few things that we need to consider when talking about point force. For the point force model, we need to have a tilted force in order to generate love waves, because purely vertical force would not generate any love waves. So we have to consider that the force will be tilted. And if it is tilted, there's some hope that at some places in terms of polarity, we're going to have a switch of polarity, because it's not exciting the whole ground the same way. It has to be tilted, and so at some point there's going to be a polarity switch somewhere, maybe in the body waves, because the body wave signal is really ugly. With the Hunga-Tonga, we have no high frequencies really, and there's so much noise in the data that I wouldn't pick anything as the first break. It makes things a bit hard. So maybe to tackle the issue, we might want to look at the simpler cases, potentially known explosions, known nuclear tests, and try methodology there and see what's possible to do for the Hunga-Tonga. And I haven't looked at other geophysical data like GNSS.
Okay. We had another question come in from Frederick Simons. Thanks for the nice talk. I'd love for you to comment on how the magma hammer interpretation by Yingkai Zheng et al. Is consistent or at odds with your story. Is that something you're able to comment on? Are you familiar with their magma hammer interpretation?
Yeah. So I think it is at odds with our story. And so one of the things that I wanted to potentially mention is that I'm going to try to go back. If you remember when I was looking at those, let me do this. Here it is. If we look at this, so most of the magma hammer theory is based on interpretation and modeling from a source time function that is obtained from teleseismic body wave stack. And I don't know if they noticed or not that there's some surface wave coming in exactly at the moment where we stack all of those body wave signals, and potentially this might have influenced the whole story. So I'm very cautious when it comes with those body wave signals, because we don't have a lot of low frequencies of high frequencies. It's also very difficult to tell exactly where the signal starts. And it seems that with a very simple model with some short impulse sources, we're able to fit the whole data sets. Because we have to filter the data quite heavily, I'm very hesitant with trying to interpret what I see with the source time function. So I think we're on a disagreement with Yingkai.
Okay, we've got another source-related question here from Darren. It says, great talk. Curious about your hypothesis about a repeating source or sub-event mechanism. Wouldn't we expect the dramatic volcanic process to be destructive in nature? Do you have any ideas as how this can be better reconciled or tested?
This is a good question. So don't know exactly. So what's certain is that it damaged a lot the caldera. So there's a 800 meters hole underwater now, where it was almost flat under the water. So this left a huge hole in the ground, and I don't know at which point does this get into the way of how it started and how we had this repeating process. So if we have the repeating process, it means that if we consider the point force, for instance, it means that we had the buildup of pressure, the cap that breaks, and at some point it gets closed again. So the buildup can start again, and we could have other repeated sources. If we have the explanation from the phreatomagmatic interactions, where we have buildup of steam and pressure directly within the rocks, and chain reaction, maybe it's more plausible to have repeated chain reactions there, but I'm not a volcanologist. I'll be honest.
Okay. We had a question come in here from Felix, which is something I was also thinking about. It says the ambiguity between force, source, and moment tensor could have been resolved. Do you think that could have been resolved if there had been some near field data? In addition, does that ambiguity arise because the orientation of the force is vertical? That is, like a different orientation of the source could still be solved with a moment tensor model.
Yeah, absolutely. I think so if we had for instance, horizontal force, which was the case for Mount St. Helens, during the Mount St. Helens eruption, there's this huge landslide, which is very well modeled with a point force that's near horizontal. This is basically a huge dipole that drags in one direction and pushes in the other one. And so looking at polarities, this would be a totally different pictures. We wouldn't have those coherent signal all across the network. So that's for the orientation. So I think the fact that it's vertical plays a lot. And if we had some good quality data nearby, potentially we might have picked some additional information. I don't know if it would have been enough to just completely lift the ambiguity, because it seems to be also present when we if you look at the North Korea explosion, which is well instrumented. We have station almost nearby. Well, it's a interesting story as well. We have this ambiguity as well.
Okay, few additional questions. So Thornley writes in and says, for the contained explosion model, 1 kilometer deep, what is the physical process? What is the source time function you assume? Is it an impulse? He says volcanic explosion fragmentation of a plug generally involves expulsion of material and is not contained at depth. So body force representations are only valid if the physical process is accurately captured.
I'm not sure I understand the question completely. I'll try to do my best answering. So we have this, so we kept this short impulse model. We were able to fit the data with longer sources as well. And we basically kept the simplest one. So we think we don't have that much resolution on the exact duration of the sources, at least when we study the surface waves. Same thing with the body waves, because under 10 seconds filtering, we start to lose coherency in the signal. So we'll at least keep this ambiguity for like a 10-second resolution, perhaps a bit more. So I don't think we can tell precisely exactly the duration of each of the pulses. And one of the reasons we kept the result at 1 kilometer, potentially there's also some numerical modeling consideration involved. If you place a moment, so the point force at the surface is no problem, but with the moment tensor exactly at the surface, there might be some issues with the numerical solvers. So just to be safe, we kept everything in 1 kilometer. And I think at those distances, when we considering, so the closest station we have is more than 700 kilometers away. And at those distances and at the filtering that we have, I don't think we can have the resolving power to say it's at 50 meters or at 200 meters.
Another question about the source here from Rodrigo. It says, thanks for the great talk. What do you think about the depth of the seismic sources? Is that something that needs to be reviewed? It says, I'm wondering about shallow sources when the fragmentation already started happening, as you showed in the decoupling section. And also, how does how does the station cover the stereographic net? Is it evenly covered in terms of the data?
So we don't have a even coverage for the surface wave. The coverage, at least in terms of azimuthal gap, is good for the teleseismic. We have lots of station on the American side of things. But again, because we have so much trouble looking at the body waves at teleseismic distances without filtering, there's a direct trade-off between what you could do with those distance signals filtered and what we can tell in terms of where the depth is. So we've done some depth search actually in the paper. And except for the surface wave and moment tensor case, we saw that we have a really bad sensitivity to depth. So here we used the teleseismic body waves, and we did a grid search for all possible force orientation up until 60 kilometer depth. And the best one was at more than 25 kilometers. So this is with the surface waves. So the best force is at about 11 kilometer depth. The P wave for the moment tensor, so the best sources is at between 10 and 15 kilometer, and it's only with the surface wave data that we were able to have a solution that at least is sensible in terms of where it sits compared to the volcano, because it's unlikely it's a very deep process. So that's why we have chosen to stick with 1 kilometer depth throughout the rest of the analysis. It's because this was the output of this depth search for the surface wave moment tensor grid search. And we thought it was at least a good compromise between the lack of depth resolution and what we believe happened at the volcano.
Okay, we have a few additional questions that have come in here. So Zheng Chen writes in and says, I'm interested in a question that can the wave equation of elastic medium be used to calculate the fluctuation of atmospheric pressure? So is it possible to use software such as QSSP or FK to simulate changes in atmospheric pressure? I don't know if you'd be able to comment on that portion of the data set.
Yeah, we have people in the group working on atmospheric to ground coupling with acoustic sources. So it's definitely possible with codes like SpecFem. You have fluid-solid interfaces. The problem is the atmospheric pressure disturbance. The period is, I think, more than half an hour. I think it's a very long period data. So we have a really bad resolution on the origin time. So I think, unfortunately, the seismic is probably the best we have in terms of determining what the best origin is, but still the data set is troublesome to work with.
We had an anonymous question come in about the sub events that happened to the events 2, 3, and 4. Just wondering if evacuation and return of seawater from the event area has that been considered as an explanation for those events?
Potentially, and one way to be able to tell that would be to use tsunami modeling, because this would, if there's a huge hole that's punched in the water column before the water gets back, this is going to be tsunamogenic. So this would be interesting to see whether it can fit any of the arrivals that were recorded in the surrounding area.